Hello everybody, my name is Nizar Habash. I'll be talking to you today about computational morphology and lexicography modeling of modern standard Arabic nominals. This is work done at New York University, Abu Dhabi at the Camel Lab with Christian Khairallah, Reham, Marzouk, Salam, Khalifa, and Mayar, Nassar. So why are we talking about morphology in the age of neural models and large language models? Well, it turns out that morphological analyzers still do have an added value in several NLP tasks, like grammatical error correction, controlled generation, morphological disambiguation, and even machine translation. Particularly, this is true with low-resource languages and also morphologically rich languages. They could be used as filtering methods, as feature sources, as augmentation support, and also for explainability. Particularly the work that we're presenting here fits under a project called the Camel Morph project, which has a big goal of building open source Arabic morphological models that maximize coverage of Arabic linguistic phenomena for standard classical and dialectal Arabic. And these models are designed so that they can be readily usable within an existing Python open source suite for Arabic NLP called Camel Tools. Specifically, the contributions of this paper is defining the space of challenges in modeling modern standard Arabic, MSA nominals, which are not typically studied as much or talked about as much, as well as developing an extendable large-scale implementation using Camel tools and benchmarking these models also, and we make all of our code and data publicly available. So Arabic morphology has a lot of challenges, such as its richness, its complexity, the multiple dialectal variations, as well as orthographic ambiguity and orthographic inconsistency. Specifically, when we talk about nominals, we're going to focus on morphological challenges like the rich and complex morphology, particularly templatic and concatenative morphology and interactions between these different features, as well as the form function mismatch problems such as broken plurals, irregular gender, different case variants, and syncretism. From the lexicographic point of view, we also are concerned with issues like paradigm incompleteness, the multiple forms of stems that are available, and interparadigm ambiguity that needs to be modeled well. Let's take an example here, and this is heavily reduced from the fullness that you would find, of course, in the available data that we make available to you. Here, we're looking at a small table of combinations of forms and functions. We're looking at 4 features: gender, number, case, and state. We're not showing the dual number, and we're also not showing the accusative state. And then each band that is colored represents, let's call it a morpheme group, that basically captures a particular behavior that we know happens in Arabic. So when we talk about the small letters M, S, and I, we're talking about masculine singular, nominative, indefinite. And when we talk about plus capital MS, that is basically the masculine singular group of morphemes by form. The table shows here the default mapping of form and functions. This is when everything goes well. In practice, this doesn't happen all the time, although so an example would be the first case of employee that is beautifully regular, but then you get examples like Safir, the second example, or ambassador, which looks almost regular in its mapping, except it has a broken plural, Sufara, which is the second row that appears in its cluster. And here, the plurality is indicated in the stem because it comes from a pattern. But then the features to express the rest of the information, like the case and the state, that is done using a masculine singular suffix in that case. Other examples are things like Nar, fire, and Khalifa, caliph, which actually both flip the gender. For example, Khalifa is masculine, but it takes a feminine singular suffix, and its plural takes a masculine singular suffix. So all of these are aspects that we need to model within our solution. Now, when we put it all together, let's take this example, which we use in the paper, of the ambassador example, where there is Safir and Suhra. And the two examples we contrast are both in English we translate as "and for their ambassadors," except the top one is feminine, the bottom one is masculine. وَلِسَفِيرَاتِهِمْ وَلِسُفَرَائِهِمْ. And the first thing, of course, we note is the use of the sound versus broken plurals, where it's not just affecting the stem, but affects also what suffixes would appear and what is the meaning of the features aligned with the suffixes. So the suffix in the top example, ati, basically captures gender, number, case, and state, but in the bottom part, it only captures the case and state of the suffix, and the gender and the number are actually part of the stem in that case. Secondly, if we look at the interactions between these different forms, we will note also that there are different spellings of the stem. So sufara, if you see it at the top, it appears with one particular spelling, and then it appears later with a different spelling that we separate into what we call a buffer that basically marks interactions between the stem and the rest of the suffixes. We also note that the enclitic that indicates the possessive pronoun there, as in their ambassadors, also has different forms, and those also are variable. To kind of give a quick cheat sheet on the side, these are all the possible forms in this case. So there are actually 3 different spellings that vary depending on whether we actually have the enclitic or not, the case ending, and that's how we would model all of these combinations with each other. Finally, I want to point out the issue of these 2 lines that I'm marking in red and in green, which represent 2 different ways for how to model the morphology. The top one is the Buckwalter database, which is basically what is used inside of Camel Tools, inside of the SAMA, the Standard Arabic Morphological Analyzer system from the LDC. And this thinks of Arabic as basically having 3 regions of complex prefixes, complex suffixes, and stem, and their combination with each other. Within the Camel Morph specification, we opt to represent these in smaller units that then combine automatically. And that basically gives us more power of control to decide and update and change instead of changing entries in a database of suffixes that basically encode all the combinations by hand. This gets me to the Camel Morph approach, where basically we would have the Camel Morph specifications that specify things like the order, the lexicon entries, the morphology, and additional regex also that can help with cleanup of the forms. Then we have a piece called the database maker, and this is this component here that compiles, if you may, into the form of the prefix, stem, suffix, and their compatibilities that are used in the Buckwalter approach and inside of the Camel Tools system. So you can think of this as basically living in between 2 worlds. In one case here we have linguistic representations and rules that are very top-down, high-level, and these are the bottom-up approaches that are kind of more optimized toward speed and efficiency of modeling in both morphological analysis and generation. Now, to make it more concrete, as much as we can within the time limit that we have here, just looking at these specific examples, we point out first, the order aspect, which basically tells us there are different classes of morphemes. So the determiner, the noun stems, the noun buffer, and then the nominal suffixes and the pronouns. And each one of the order lines basically tells us what can actually fit in that position. Now, that is, of course, not enough because this suggests certain combinations can happen that don't actually happen. For that, we need what we call truth conditions. And these truth conditions are basically ad hoc named symbols, where basically they are set to be true and then required to be true. And when everything within a particular word has been set to be true, all the requirements are fulfilled, that word is considered to be a valid word. Otherwise, it's not allowed. That's how what the DB maker uses to basically determine whether a compatibility is present or not. So in this particular example, there are these 4 different truth conditions that all basically come together and allow us to say that this word can actually happen. Now, this is clearly an intensive effort. It was done with semi-automatic processes and involved a number of annotators working on both the morphology and lexicographic design. The specifications that we have are about 27,000 lemmas, and they're associated about 33,000 or so stems. The number of prefixes is about 18 with 20 variants, and 99 for the suffixes with 197 variants. And there were about 51 truth conditions that we actually used for the nouns. The nouns were quite complex. When we build our database automatically, we can then compare it to Kalima MSA, which is basically based on Bama and Sama. And this was slightly different implementation, but it's quite comparable. And we can compare our DB to it. And of course, we note here that the number of lemmas is about the same. The number of the stems in our specification is much lower. So we have 33,000 versus 37, almost 38,000 in the other databases. And that basically suggests that when a linguist is working on developing these systems, it's easier for them to actually update and manipulate. Of course, also in the terms of the number of forms and analysis, we have a lot more. That's because we added and extended some features and affixes that were not present in the other systems. We reported the paper on a coverage evaluation against the Pan-Arabic tree bank, showing that we have 95% recall of analyses and that 86% of the mismatches were due to gold errors. Now, in conclusion, we presented to you a review of the challenges in modeling MSA nominals, developed benchmarks for large-scale implementation, and we make all of this publicly available. We plan to work on other part of speech and other Arabic dialects. We also want to take other challenges like noisy spelling, dialectal, interword code switching, template-based backoff, automatic learning of lexicon entries. All of this is, of course, enabled by the modeling decisions that we've made so far. We also plan to evaluate our models on downstream applications. And thank you very much. I look forward to your questions. I'll see you at the conference.